A wave function or wave function, also named a state function, in quantum mechanics describes the quantum state of a system of one or more particles and contains all the information about the system. Quantities associated with measurements, like the average momentum of a particle, are derived from the wave function. Thus it is a central quantity in quantum mechanics. The most common symbols for a wave function are the Greek letters, or, lowercase and capital Psi. The Schrödinger equation determines how the wave function evolves over time, that is, the wave function is the solution of the Schrödinger equation. The wave function behaves qualitatively like other waves, like water waves or waves on a string, because the Schrödinger equation is mathematically a type of wave equation. This explains the name wave function and gives rise to wave-particle duality. The wave function for a given system does not have a unique representation. Most commonly, it is taken to be a function of all the position coordinates of the particles and time, that is, the wave function is in position space. However, we could also consider a wave function in momentum space a function of all the momenta of the particles and time instead. In general, the wave function of a system is a function of continuous and discrete variables characterizing the system's degrees of freedom, and there is one wave function for the entire system, not a separate wave function for each particle in the system. Elementary particles, like electrons, have spin, and the wave function must include this fundamental property as an intrinsic degree of freedom. The wave function is spinorial for fermions, namely particles with half-integer spin, 1/2, 3/2, 5/2, or tensorial for bosons, particles with integer spin, 0, 1, 2, 3. In most treatments of quantum mechanics, the wave function is complex-valued. In one important interpretation of quantum mechanics called the Copenhagen interpretation, the modulus squared of the wave function, vertical bar 2, is a real number interpreted as the probability density of finding a particle in a given place at a given time, if the particle's position is to be measured. Since the wave function is complex-valued, only its relative phase and relative magnitude can be measured. It does not directly tell anything about the magnitudes or directions of measurable observables. One has to apply quantum operators to the wave function and find the eigenvalues which correspond to sets of possible results of measurement. However, complex numbers are not necessarily used in all treatments. Louis de Broglie in his later years proposed a real-valued wave function connected to the complex wave function by a proportionality constant, and developed the de Broglie-Bohm theory. The unit of measurement for depends on the system. For one particle in 3 dimensions, its units are length 3/2. These unusual units are required so that an integral of vertical bar 2 over a region of 3-dimensional space is a unitless probability, the probability that the particle is in that region. For different numbers of particles and /or dimensions, the units may be different and can be found by dimensional analysis. In the 1920s and 1930s, quantum mechanics was developed using calculus and linear algebra. Those who used the techniques of calculus included Louis de Broglie, Erwin Schrödinger, and others, developing wave mechanics. Those who applied the methods of linear algebra included Werner Heisenberg, Max Born, and others, developing matrix mechanics. Schrödinger subsequently showed that the two approaches were equivalent. In each case, the wave function was at the center of attention in two forms, giving quantum mechanics its unity. In 1905, Planck postulated the proportionality between the frequency of a photon and its energy in the Planck-Einstein equation, E=hf. In 1925, de Broglie published the symmetric relation between momentum and wavelength, E=h/p, now called the de Broglie relation. These equations represent wave-particle duality. In 1926, Schrödinger published the famous wave equation now named after him, indeed the Schrödinger equation, based on classical energy conservation using quantum operators, and the de Broglie relation such that the solutions of the equation are the wave functions for the quantum system. Later Pauli invented the Pauli equation, that adds a description of electron spin, and magnetic dipole. However, no one, even Schrödinger or de Broglie, were clear on how to interpret it. Around 1924-27, Max Born, Heisenberg, Bohr, and others provided the perspective of probability amplitude. This is the Copenhagen interpretation of quantum mechanics. There are many other interpretations of quantum mechanics, but this relates calculations of quantum mechanics directly to probabilistic experimental observations. In 1927, Hartree and Fock made the first step in an attempt to solve the n-body wave function and developed the self-consistency cycle, an iterative algorithm, to approximate the solution. Now it is also known as the Hartree-Fock method. The Slater determinant and permanent of a matrix was part of the method provided by John C. Slater. Schrödinger did encounter an equation for the wave function that satisfied relativistic energy conservation before he published the non-relativistic one, but discarded it, as it predicted negative probabilities and negative energies. In 1927, Klein-Gordon and Fock also found it, but incorporated the electromagnetic interaction and proved that it was Lorentz invariant. De Broglie also arrived at the same equation in 1928. This relativistic wave equation is now most commonly known as the Klein-Gordon Equation. In 1927, Pauli phenomenologically found a non-relativistic equation to describe spin 1/2 particles in electromagnetic fields, now called the Pauli equation. Pauli found the wave function was not described by a single complex function of space and time, but needed two complex numbers, which respectively correspond to the spin plus 1/2 and 1/2 states of the fermion. Soon after, in 1928, Dirac found an equation from the first successful unification of special relativity and quantum mechanics applied to the electron, now called the Dirac Equation. In this, the wave function is a spinor represented by four complex-valued components. Spin was an automatic consequence of this wave function. Later, other wave equations were developed. See relativistic wave equations for further information. Wave functions and function spaces. Functional analysis is commonly used to formulate the wave function with the necessary mathematical precision. Usually they are quadratically integrable functions, at least locally, because it is compatible with the Hilbert space formalism mentioned below. The set on which their function space is defined is the configuration space of the system. In many situations it is a Euclidean space. That implies that wave functions are functions of several real variables. Superficially, this formalism is simple to understand for the following reasons. If the wave function is to change throughout space and time, one would expect the wave function to be a function of the position and time coordinates. It is solved from the Schrodinger equation, or other relativistic wave equations, a linear partial differential equation. Functions can easily describe wave-like motion using periodic functions, and Fourier analysis can be readily done. Functions are easy to produce, visualize, and interpret because of the pictorial nature of the graph of a function. One can plot curves, surfaces, contour lines, more generally any level sets. If the situation is in a high number of dimensions, one can analyze the function in a lower dimensional slice to see the behavior of the function within that confined region. For concreteness and simplicity, in this article, when coordinates are needed, we use Cartesian coordinates, so that R is short for x, y, z, although spherical polar coordinates and other orthogonal coordinates are often useful to solve the Schrödinger equation for potentials with certain geometric symmetries, in which case the position and wave function is expressed in these coordinates. One does not have to define wave functions necessarily on real spaces. Appropriate function spaces can be defined wherever a measure can provide integration. Operator theory and linear algebra, as shown below, can deal with situations where the real analysis is not applicable. Requirements: continuity of the wave function and its first spatial derivative in the x direction, y, and z coordinates not shown at some time t. The following constraints on the wave function are formulated for the calculations and physical interpretation to make sense. It must everywhere be a continuous function and continuously differentiable. It must everywhere satisfy the relevant normalization condition, because the particle or system of particles exists somewhere with 100% certainty. For this to be so, the wave function must be square integrable. A requirement less restrictive is that the wave function must belong to the Sobolev space W1, 2. It means that it is differentiable in the sense of distributions, and its gradient is square integrable. This relaxation is necessary for potentials that are not functions, but are distributions, such as the Dirac delta function. If these requirements are not met, it is not possible to interpret the wave function as a probability amplitude. Definition: one spinless particle in 1D. Standing waves for a particle in a box, examples of stationary states. Traveling waves of a free particle. The real parts of position and momentum wave functions, x and p, and corresponding probability densities vertical bar, x, vertical bar 2 and vertical bar, p, vertical bar 2, for one spin 0 particle in one x or p dimension. The wave functions shown are continuous, finite, single-valued and normalized. The color opacity, % of the particles corresponds to the probability density, not the wave function, of finding the particle at position x or momentum p. For now, consider the simple case of a single particle without spin, in one spatial dimension. More general cases are discussed below. Position space wave function. The state of such a particle is completely described by its wave function, where x is position and t is time. This is a complex-valued function of two real variables x and t. If interpreted as a probability amplitude, the square modulus of the wave function is the positive real number. Interpreted as the probability density, that the particle is at x, rather than some other location. The star indicates complex conjugate. If the particle's position is measured, its location is not deterministic, but is described by a probability distribution. The probability that its position x will be in the interval xb is the integral of the density over this interval, where t is the time at which the particle was measured. This leads to the normalization condition. Because if the particle is measured, there is 100% probability that it will be somewhere. Since the Schrödinger equation is linear, if any number of wave functions and for n equals 1, 2, are solutions of the equation, then so is their sum, and their scalar multiples by complex numbers n. Taking scalar multiplication and addition together is known as a linear combination. This is the superposition principle. Multiplying a wave function by any non-zero constant complex number c to obtain c does not change any information about the quantum system, because c cancels in the Schrödinger equation for c. All that happens is that any normalization constant will be rescaled. Since linear combinations of wave functions obtain more wave functions, the set of all wave functions w equals x, t, is an infinite-dimensional vector space over the field of complex numbers. To form a vector space basis B, we need a maximal set of wave functions 1, 2, and W which are linearly independent. Each one of them is not a linear combination of the others. For example, 1z22 plus z33 plus and 2z11 plus z33 plus, etc. for any complex number zn, and every function in W is a linear combination of functions in B. This linear independence allows a linear combination of 1, 2. To uniquely construct an arbitrary wave function in W. In this way, x, t, can be viewed as an infinite-dimensional vector, where the complex-valued coefficients n are the components of the vector. The choice of which wave functions to use as a basis is not unique, but if a change of basis is made, the components n need to change to compensate. Momentum space wave function. The particle also has a wave function in momentum space, where p is the momentum in one dimension, which can be any value from to plus, and t is time. All the previous remarks on superposition, normalization, etc. apply similarly. In particular, if the particle's momentum is measured, the result is not deterministic, but is described by a probability distribution. And the normalization condition is relation between wave functions. The position space and momentum space wave functions are Fourier transforms of each other, therefore both contain the same information, and either one alone is sufficient to calculate any property of the particle. As elements of abstract physical Hilbert space, whose elements are the possible states of the system under consideration, they represent the same object, but they are not equal when viewed as square integrable functions. A function and its Fourier transform are not equal. For one dimension. Sometimes the wave vector k is used in place of momentum p, since they are related by the de Broglie relation. And the equivalent space is referred to as k-space. Again, it makes no difference which is used since p and k are equivalent up to a constant. In practice, the position space wave function is used much more often than the momentum space wave function. The potential entering the Schrodinger equation determines on which basis the description is easiest. For the harmonic oscillator, x and p enter symmetrically, so there it doesn't matter which description one uses. Definitions, other cases. The electron probability density for the first few hydrogen atom electron orbitals shown as cross-sections. These orbitals form an orthonormal basis for the wave function of the electron. Different orbitals are depicted with different scale. Traveling waves of two free particles, with two of three dimensions suppressed. Top is position space wave function, bottom is momentum space wave function, with corresponding probability densities. Following are the general forms of the wave function for systems in higher dimensions, and more particles, as well as including other degrees of freedom than position coordinates or momentum components. The position space wave function of a single particle in three spatial dimensions is similar to the case of one spatial dimension, above. Where r is the position vector in three-dimensional space, and t is time. As always, r, t, is a complex number, for this case a complex-valued function of four real variables. If there are many particles, in general there is only one wave function, not a separate wave function for each particle. The fact that one wave function describes many particles is what makes quantum entanglement and the PR paradox possible. The position space wave function for n particles is written where r is the position of the ith particle in three-dimensional space, and t is time. Altogether, this is a complex-valued function of 3n, plus 1 real variables. For a particle with spin, the wave function can be written in position spin space, as where r is a position in three-dimensional space, t is time, and sz is the spin projection quantum number, along the z-axis. The z-axis is an arbitrary choice, other axes can be used instead if the wave function is transformed appropriately, see below. The sz parameter, unlike r and t, is a discrete variable. For example, for a spin 1/2 particle, sz can only be plus 1/2, or 1/2. And not any other value. In general, for spin s, sz can be s, s1, s. It is convenient to write the wave function as a column vector, in which there are as many entries in the column vector as there are allowed values of sz, and the entries are indexed by the spin quantum number. For spinless wave functions, star is the complex scalar needed for normalization, but for spin wave functions the Hermitian conjugate, complex conjugate of the transpose of the column vector into a row vector, is required to obtain the real number. The ordering of and does matter, see matrix multiplication. Since the position and spin degrees of freedom of the particle are separate from one another, the wave function is a product of a purely position space wave function and a purely spin-dependent function. The wave function for n particles each with spin is, and the wave function is a product of a position space wave function and a spin-dependent function. Concerning the general case of n particles with spin in third, if is interpreted as a probability amplitude, the probability density is and the probability that particle 1 is in region R1 with spin SZ1 equals M1 and particle 2 is in region R2 with spin SZ2 equals M2 etc. at time t is the integral of the probability density over these regions and spins. The multidimensional Fourier transforms of the position or position spin space wave functions yields momentum or momentum spin space wave functions. The inner products of these momentum space wave functions are similar to the position cases above, with the corresponding normalization conditions. Inner product. Position space inner products. The inner product of two wave functions 1 and 2 is useful and important for a number of reasons given below. For the case of one spinless particle in 1D, it can be defined as the complex number at time t. More generally, the formulae for the inner products are integrals over all coordinates or momenta and sums over all spin quantum numbers. That is, for one spinless particle in third, the inner product of two wave functions can be defined as the complex number, while for many spinless particles in third, altogether, this is n three-dimensional volume integrals over the regions R4I equals 1, and, with differential volume elements D3, also written dVi, or dxi dyi dzi, for one particle with spin in third, and for the general case of n particles with spin in third. Altogether, n three-dimensional volume integrals over the regions R4I equals 1, and, followed by n sums over the spins. In the Copenhagen interpretation, the modulus squared of the inner product, a complex number, gives a real number, which is interpreted as the probability of the wave function 2 collapsing to the new wave function 1 upon measurement of an observable, whose eigenvalues are the possible results of the measurement, with 1 being an eigenvector of the resulting eigenvalue. Although the inner product of two wave functions is a complex number, the inner product of a wave function, with itself, is always a positive real number. The number vertical bar vertical bar vertical bar vertical bar, not vertical bar vertical bar vertical bar vertical bar 2, is called the norma of the wave function, and is not the same as the modulus vertical bar vertical bar. A wave function is normalized if is not normalized, then dividing by its norm gives the normalized function slash vertical bar vertical bar vertical bar vertical bar. Two wave functions 1 and 2 are orthogonal if their inner product is 0. A set of wave functions 1, 2 are orthonormal if they are each normalized and are all orthogonal to each other, where m and n each take values 1, 2, and mn is the Schrödinger delta, plus 1 for m equals n and 0 for mn. Orthonormality of wave functions is instructive to consider, since this guarantees linear independence of the functions. Actually, the wave functions do not have to be orthonormal, and can still be linearly independent, but the inner product of m and n is more complicated than the Riemann. Returning to the superposition above, if the basis wave functions n are orthonormal, then the coefficients have a particularly simple form. If the basis wave functions were not orthonormal, then the coefficients would be more complicated. Momentum space inner products. Analogous to the position case, the inner product of two wave functions 1, pt, and 2, pt, can be defined as, and similarly for more particles in higher dimensions. One particular solution to the time-independent Schrodinger equation is a plane wave, which can be used in the description of a particle with momentum exactly p, since it is an eigenfunction of the momentum operator. These functions are not normalizable to unity, they aren't square integrable, so they are not really elements of physical Hilbert space. The set forms what is called the momentum basis. The spaces is not a basis in their usual mathematical sense. For one thing, since the functions aren't normalizable, they are instead normalized to a delta function. For another thing, though they are linearly independent, there are too many of them, they form an uncountable set, for a basis for physical Hilbert space. They can still be used to express all functions in it using Fourier transforms as described above. Distinguishable and identical particles. Further information, identical particles, wave function representation. In quantum mechanics there is a fundamental distinction between identical particles and distinguishable particles. For example, any two electrons are identical and fundamentally indistinguishable from each other. The laws of physics make it impossible to stamp an identification number on a certain electron to keep track of it. This translates to a requirement on the wave function for a system of n identical particles all of common spin s. The wave function of the system is either totally symmetric or totally antisymmetric in all the positions of the particles, where the plus sign occurs if the particles are all bosons, s equals 0, 1, 2, and sign if they are all fermions, s equals 1/2, 3/2. For in identical particles there is no such thing as mixed symmetry. The wave function cannot be symmetric for some of the particles and antisymmetric for others. Notice the physical interchange of particles corresponds to mathematically switching arguments in the wave function. The antisymmetry feature of fermionic wave functions leads to the Pauli principle. Generally, bosonic and fermionic symmetry requirements are the manifestation of particle statistics, and are present in other quantum state formalisms. For indistinguishable particles, no two being identical, there is no requirement for the wave function to be either symmetric or antisymmetric. Units of the wave function. Even though wave functions are complex numbers, both the real and imaginary parts each have the same units. The imaginary unit I is a number without unit. The units depend on the number of particles the wave function describes, and the number of spatial or momentum dimensions of the system. In general, for n particles with positions r1, r2, rn in spatial dimensions, the normalization conditions require to have units of length n/2. The square root of the length unit is removed when one finds vertical bar 2, which has units of length nn. In momentum space, length is replaced by momentum, and the units are momentum nn/2. These results are true for particles with or without spin, since for particles with spin, the summations are over dimensionless spin quantum numbers. Wave functions as elements of an abstract vector space. Quantum state. The set of all possible wave functions at any given time forms an abstract mathematical vector space. This vector space is infinite dimensional because there is no finite set of functions which can be added together in various combinations to create every possible function. Specifically, the entire wave function is treated as a single abstract vector, where vertical bar is a ket vector written in bra ket notation. As always, the state vector for the system is solved from the Schrodinger equation, or other dynamical pictures of quantum mechanics. The statement that wave functions form an abstract vector space means that it is possible to multiply wave functions by complex numbers, and add together different wave functions in a coherent superposition. If vertical bar and vertical bar are two states in the vector space, and A and B are two complex numbers, then the linear combination subject to normalization is also in the same vector space. The dual vectors are denoted as bras vertical bar, which do not live in the same space as vertical bar, but instead the dual space, where star denotes complex conjugate. The inner product of two wave functions vertical bar 1 and vertical bar 2 can be defined by. For these reasons, wave functions are elements of a Hilbert space. See the quantum state article for more explanation of the Hilbert space formalism and its consequences to quantum physics. There are several advantages to understanding wave functions as elements of an abstract vector space. All the powerful tools of linear algebra can be used to manipulate and understand wave functions. For example, linear algebra explains how a vector space can be given a basis, and in any vector in the vector space can be expressed in this basis. This explains the relationship between a wave function in position space and a wave function in momentum space, and suggests that there are other possibilities too. Bra ket notation can be used to manipulate wave functions. The idea that quantum states are vectors in an abstract vector space, technically a complex projective Hilbert space, is completely general in all aspects of quantum mechanics and quantum field theory, whereas the idea that quantum states are complex-valued wave functions of space is only true in certain situations. Following is a summary of the Brach-AET formalism applied to wave functions with general discrete or continuous bases. Discrete and continuous bases. Discrete components AC of a complex vector vertical bar A equals K AC vertical bar Ek, which belongs to a countably infinite-dimensional Hilbert space. There are countably infinitely many K values and basis vectors vertical bar Ek. Continuous components, X, of a complex vector vertical bar equals dx, X, vertical bar X, which belongs to an uncountably infinite-dimensional Hilbert space. There are uncountably infinitely many X values and basis vectors vertical bar X. Components of complex vectors plotted against index number, discrete K, and continuous X to probability amplitudes out of infinitely many are highlighted. A Hilbert space with a discrete basis vertical bar I for I equals 1, 2, and is orthonormal if the inner product of all pairs of basis KETS are given by the Kronecker delta. Orthonormal bases are convenient to work with because the inner product of two vectors have simple expressions. A wave function vertical bar expressed in this discrete basis of the Hilbert space, and the corresponding bra in the dual space, are respectively given by where the complex numbers are the components of the vector. The column vector is a useful representation in terms of matrices. The entire vector vertical bar is independent of the basis, but the components depend on the basis. If a change of basis is made, the components of the vector must also change to compensate. A Hilbert space with a continuous basis vertical bar is orthonormal if the inner product of all pairs of basis KETS are given by the Dirac delta function. As with the discrete bases, a symbol is used in the basis states. Two common notations are vertical bar, and sometimes vertical bar. A particular basis KET may be subscripted vertical bar 0, or prime vertical bar, or simply given another symbol in place of. While discrete basis vectors are summed over a discrete index, continuous basis vectors are integrated over a continuous index, a variable of a function. In what follows, all integrals are with respect to the real valued basis variable, not complex valued, over the required range. Usually this is just the real line or subsets of it. The state vertical bar in the continuous basis of the Hilbert space with the corresponding bra in the dual space are respectively given by where the components are the complex valued functions of real variable. Completeness conditions. The completeness conditions, also called closure relations, are for the discrete and continuous orthonormal bases, respectively. An orthonormal set of KETS form bases if and only if they satisfy these relations. In each case, the equality to unity means this is an identity operator, its action on any state leaves it unchanged. Multiplying any state on the right of these gives the representation of the state vertical bar in the basis. The inner product of the first state vertical bar 1 with a second vertical bar 2 can also be obtained by multiplying vertical bar 1 on the left and vertical bar 2 on the right of the relevant completeness condition. Inner product. Physically, the nature of the inner product is dependent on the basis in use, because the basis is chosen to reflect the quantum state of the system. If vertical bar 1 is a state in the above basis with components C1, C2, Cn, and vertical bar 2 is another state in the same basis with components Z1, Z2, Zn, the inner product is the complex number. If vertical bar 1 is a state in the above continuous basis with components 1, and vertical bar 2 is another state in the same basis with components 2, the inner product is the complex number, where the integrals are taken overall, and the square of the norm, magnitude, of the state vector vertical bar is given by the inner product of vertical bar, with itself, a real number. For the discrete and continuous bases, respectively, each say the projection of a complex probability amplitude onto itself is real. If vertical bar is normalized, these expressions would be unity. If the state is not normalized, then dividing by its magnitude normalizes the state too. Normalize components and probabilities. For the discrete basis, projecting the normalized state vertical bar n onto a particular state, the system may collapse to vertical bar q gives the complex number. So the modulus squared of this gives a real number. In the Copenhagen interpretation, this is the probability of state vertical bar q occurring. In the continuous basis, the projection of the normalized state onto some particular basis vertical bar is a complex valued function. So the squared modulus is a real valued function. In the Copenhagen interpretation, this function is the probability density function of measuring the observable, so integrating this with respect to between a b gives the probability of finding the system with between equals a and equals b. Wavefunction collapse. The physical meaning of the components of vertical bar is given by the wavefunction collapse postulate, also known as wavefunction collapse. If the observable s momentum and /or spin, position and /or spin, etc., corresponding to states vertical bar I has distinct and definite values I, and a measurement of that variable is performed on a system in the state vertical bar, then the probability of measuring I is vertical bar 2. If the measurement yields I, the system collapses to the state vertical bar I, irreversibly and instantaneously. Time dependence. In the Schrödinger picture, the states evolve in time, so the time dependence is placed in vertical bar according to for discrete bases, or for continuous bases. However, in the Heisenberg picture, the states vertical bar are constant in time and time dependence is placed in the Heisenberg operators, so vertical bar is not written as vertical bar, t. Position representations. State space for one spin 0 particle in 1D. For a spinless particle in one spatial dimension, the x-axis, or real line, the state vertical bar can be expanded in terms of a continuum of basis states, vertical bar x, also written vertical bar x, corresponding to the set of all position coordinates x. The completeness condition for this basis is, and the orthogonality relation is, the state vertical bar is expressed by in which the wave function described as a function is a component of the complex state vector. The inner product as stated at the beginning of this article is, if the particle is confined to a region R, a subset of the x-axis, the integrals in the inner product and completeness condition would be integrals over R. State space. Other cases. The previous example can be extended to more particles in higher dimensions and include spin. For one spinless particle in third, the basis states are vertical bar R, and any state vector vertical bar in this space is expressed in terms of the basis vectors as vertical bar R with components. For spinless particles in third, the basis states are vertical bar R1, Rn. This is the tensor product of the one particle position basis vertical bar R1, vertical bar R2, vertical bar Rn, each of which spans the separate one particle Hilbert spaces, so vertical bar R1, Rn are the basis states for the tensor product of the one particle Hilbert spaces, the Hilbert space, for the composite many-particle system. Any state vector vertical bar in this space is with components. For one particle with spin in third, the basis states are vertical bar R, Sz, the tensor product of the position basis vertical bar R, and spin basis vertical bar Sz, which exists in a new space from the spin space and position space alone. Any state vertical bar in this space is with components. For particles with spin in third, the basis states are vertical bar R1, Rn, Sz1, Szn, the tensor product of the position basis vertical bar R1, Rn, and spin basis vertical bar Sz1, Szn, which exists in a new space from the spin space and position space alone. Any state in this space is with components. If the particles are restricted to regions of position space, then the integrals in the completeness relations are taken over those regions, rather than the entire coordinate space. For the general case of many particles with spin in third, if particle 1 is in region R1, particle 2 is in region R2, and so on, the state in this position spin representation is. The orthogonality relation for this basis is. And the inner product of vertical bar 1 and vertical bar 2 is. Momentum space wave functions are similar, using the momentum vectors of the particles as continuous spaces, namely vertical bar p, vertical bar p1, p2, pn, etc. Ontology. Whether the wave function really exists, and what it represents, are major questions in the interpretation of quantum mechanics. Many famous physicists of a previous generation puzzled over this problem, such as Schrödinger, Einstein, and Bohr. Some advocate formulations or variants of the Copenhagen interpretation, e.g. Bohr, Wigner, and von Neumann, while others, such as Wheeler or Jaynes, take the more classical approach and regard the wave function as representing information in the mind of the observer, i.e. a measure of our knowledge of reality. Some, including Schrödinger, Einstein, Bohm, and Everett and others, argued that the wave function must have an objective, physical existence. The latter argument is consistent with the fact that whenever two observers both think that a system is in a pure quantum state, they will always agree on exactly what state it is in, but this may not be true if one or both of them thinks the system is in a mixed state. For more on this topic, see Interpretations of Quantum Mechanics.